Hello, everyone. In the previous two lessons, we completed the automatic measurement of CNC lathe parts. Through these lessons, we have gained a solid understanding of conventional measurement methods and challenges for axle parts, especially multi-probe measurement techniques and specific methods for measuring inner and outer cylindrical surfaces. Next, let's use simulation software to review the content we have learned and complete the expansion tasks. By the end of this lesson, I hope you will be able to proficiently use simulation software to measure the concentricity of rotor parts and accurately evaluate the results, keeping the error within plus or minus 0.025 millimeters. You should also master the measurement and evaluation methods for parallelism, be able to correctly set the evaluation parameters, and output evaluation reports that meet tolerance requirements. In the expansion tasks, we will gradually use functions like parallelism, radial runout, axial runout, and tonal runout evaluations. Let's now focus on the measurement of dimensions 7 through 10. We will use simulation software to complete these measurements. Dimension 7 is the diameter of cylinder 5, with the reference feature being our reference A, which has already been measured, so no further measurement is required here. Dimension 8 is the diameter of cylinder 6, measured using the automatic cylinder command. Dimension 9 is the concentricity, with the associated features being cylinder 7 and reference A. We only need to measure cylinder 7 here. Dimension 10 is parallelism, with the associated features being reference A and plane 4, both of which have already been measured. Let's proceed with the measurements for cylinder 6 and cylinder 7. Switch the cursor to the end of the plane 4 feature and use the automatic cylinder command to measure cylinder 6 and cylinder 7. Change the name to CYL6, set the center coordinates to 0, 140 is 0, the inner cylinder diameter to 46, and the length to 10. Enable arc movement switch and show contact point switch. Set contact path properties to 6 points per layer, with a depth of 2, and ending depth of 2. We measure 2 layers. Click Create to complete the measurement of cylinder 6. Similarly, we use the automatic cylinder command to measure cylinder 7. Change the name to CYL7, set the center coordinates to 0, 148, 0, the inner cylinder diameter to 60, and the length to 8. Enable arc movement switch and show contact point switch. Set contact path properties to 6 points per layer, with a depth of 2, and ending depth of 2. We measure 2 layers. Click Create to complete the measurement of cylinder 7. Next, dimensional evaluation. Position the cursor at the end of the program and click on Position Evaluation. Deselect the automatic option and select the evaluation items that need to be checked. Change the name to DF007. Select reference A and the diameter. The nominal value is 35, with an upper tolerance of plus 0.05 and a lower tolerance of minus 0.025. Click Create to complete the evaluation for dimension 7. Similarly, we need to complete the evaluation for dimension 8. Select cylinder 6 and the diameter. The tolerance values are 46, with an upper tolerance of plus 0.021 and a lower tolerance of minus 0.049. Change the name to DF008. Click Create to complete the evaluation for dimension 8. Dimension 9 is the concentricity, with the associated features being reference A and cylinder 7. Click on the evaluation in concentricity, select the 7th cylinder, then click on the reference definition and choose CYLA2 as the reference A. Click Create and close the concentricity evaluation window. Note that the tolerance is plus 0.025. Click the plus button to add reference A, rename it to CO009. And click Create to complete the evaluation for concentricity. Next is the evaluation of the 10th dimension, parallelism, with the associated features being our plane 4 and reference B. Click on the parallelism evaluation, select PLN4, and rename it to PA010. Click the plus button to define our plane B as reference B, and define PLNB2 as reference B. Then, click the Create button and close. Switch the reference to B. Set the tolerance to plus 0.025 and choose PLN4 as the evaluation object. Click Create to complete the evaluation for parallelism. After completing the dimensional evaluations, press Ctrl+Q to execute all programs. Then, go to View Report window in the menu to print the evaluation report. Next, let's look at the measurement and application of common reference elements. 1. Common reference axis. As shown in Figure 6.35, when a common reference axis is formed by the combination of two or more axes, the reference is determined by a set of cylindrical or conical surfaces that satisfy coaxial constraints on the exterior of the solid. Simultaneously, the features with their extracted components, or extracted cylindrical or conical surfaces, of each reference element are fitted, and the orientation features, or derived features, of the fitted components are established. The common reference axis is the derived feature, orientation feature of the fitted component, shared by these extracted components. 2. Common reference plane. As shown in Figure 6.36, when a common reference plane is formed by the combination of two or more surfaces, the reference is determined by a set of planes that satisfy directional or positional constraints on the exterior of the solid. Simultaneously, the features with their extracted components, or extracted surfaces, of each reference element are fitted, and the orientation features of the two fitted planes are established. The common reference plane is the orientation feature of the fitted components shared by these extracted surfaces. 3. Common reference center plane. As shown in Figure 6.37, when a common reference center plane is formed by the combination of two or more sets of parallel planes, the reference consists of two or more sets of parallel planes that satisfy the parallel and symmetric center plane coplanarity constraints on the exterior of the solid. Simultaneously, the features with their extracted components, the extracted surfaces from the two sets of each reference element are fitted, and the orientation features, or derived features, of the fitted components are established. The common reference center plane is the derived feature, orientation feature of the fitted component, shared by these fitted components. During the measurement of the common reference, the elements involved in establishing the common reference have equal roles in positioning and orientation. Therefore, they can be treated as a single element for measurement purposes. For example, in the following diagram, when measuring with reference A, multi-layer cross-sectional circles are used, applying the midpoint of each circle layer. The same operation is performed with reference B. Finally, all the midpoints obtained by applying the construct point function are fitted, using the construct line function, to form a 3D spatial axis. The 3D line serves as the common reference element, as shown in Figure 6.38. Through today's lesson, not only have we reviewed the measurement techniques we learned before, but more importantly, we have successfully mastered the measurement and evaluation methods for geometric tolerances such as concentricity and parallelism for rotors. Through hands-on practice with simulation software, we have deepened our understanding of these key measurement tasks and improved our measurement accuracy and efficiency. Finally, please reflect on this lesson and complete the following exercises to consolidate the knowledge you learned today and deepen your understanding. That concludes today's lesson. See you next time.